Hey there, curious minds. Welcome to another deep dive, where we shortcut your journey to being well-informed. Today, we're plunging into a topic fundamental to life itself, the structure and function of the reproductive systems. We're navigating a comprehensive chapter from Understanding Pathophysiology, 7th edition, by Huether, McCants, Brashers, and Rote. Our mission is to unpack the intricate details of how these systems develop, what they do, and how they change over a lifetime, all in an engaging way that lets you grasp the most important insights without needing a single visual.
Yeah, think of us as your expert navigators through this complex biological landscape.
Exactly.
It's a truly remarkable journey we're embarking on, one that reveals the incredible precision and, orchestration of the human body. We'll be tracing the development of these systems right from their earliest embryonic stages.
The very beginning.
Right. Exploring the powerful roles of key hormones, delving into the distinct anatomies of both male and female bodies, and even examining the effects of aging. Understanding these foundational elements is absolutely crucial for anyone studying health and disease, and I think we'll uncover some truly surprising facts along the way.
I love that surprising facts. So let's start at the very beginning. Before any of us even knew we were coming, we're talking embryonic sexual differentiation.
Okay.
It's wild to think that male and female embryos actually begin with identical or homologous reproductive structures. Tell us, what does that early, undifferentiated stage look like?
It's a fantastic starting point because it reveals a profound biological truth. Initially, all embryos possess one pair of primary sex organs, known as gonads,
Right.
and two pairs of ducts, the Wolffian ducts and the Müllerian ducts. These are like the raw materials for both sexes.
Okay, so if we all start with the same basic kit, what's the switch? What sends us down either the male or female path? Is there a specific point where that decision is made?
Absolutely. Imagine a critical fork in the road, around 6 to 7 weeks of gestation. The presence of a specific gene on the Y chromosome called SRY is the decisive factor. When this SRY gene expresses a protein called test-determining factor, or TDF, it triggers male gonadal development. What's truly insightful here is that the default blueprint, for human development, in a sense, is female.
Really? The default is female?
Yeah. The SRY gene acts not just as a switch, but as a specific override to that default. It fundamentally shapes half of the human population. It reveals a remarkable plasticity in our earliest developmental stages.
That's a mind-blowing way to think about it, a biological override. So if that override is activated and we're heading towards male development, what happens next? What do these developing testes do?
Well, once those developing testes form, they immediately get to work. They secrete testosterone,
Right.
which promotes the Wolffian ducts to develop into male internal organs like the epididymis and the vas deferens. But that's not all. They also secrete something called Müllerian inhibitory hormone, or MIH.
MIH, Müllerian inhibitory. So it stops the Müllerian ducts.
Exactly.
Yeah.
As the name suggests, MIH causes those Müllerian ducts, which would otherwise become female internal organs, to simply degenerate. A double action mechanism, promoting one path while actively suppressing the other.
Wow. Okay. And if that SRY gene isn't present, if there's no TDF, then it sounds like the system just continues on its original default female trajectory.
Precisely. In the absence of the SRY gene, female development proceeds naturally. The two gonads develop into ovaries.
Go.
Without testosterone to support them, the Wolffian ducts degenerate. Crucially, without Müllerian inhibitory hormone, the Müllerian ducts maintain themselves, forming the fallopian tubes, uterus, cervix, and the upper two-thirds of the vagina.
So they just keep going.
They just keep going. Even the external structures follow this pattern. The genital tubercle differentiates into male genitalia only with testosterone. Otherwise, female genitalia develop. It's like the body follows a precise set of instructions, and a lack of one key instruction keeps it on the initial path.
Incredible. So we've got the foundational structures formed. Let's fast forward a bit from embryonic development to another monumental stage of change, puberty. What exactly marks the onset of puberty, and how is it different from just growing up into adolescence?
That's an excellent distinction to make. Puberty is specifically the onset of sexual maturation, the biological changes leading to reproductive capability. Adolescence is broader, right? It includes those biological changes, but also significant social and psychological development.
Got it.
The timing of puberty itself is fascinatingly variable, influenced by a blend of genetics, nutrition, even environmental factors. For females, it often begins around 8 to 9 years old with the LARSH, or breast development.
The large, okay.
Males typically start a bit later, maybe around 11 years.
So what's the ultimate orchestrator behind this remarkable transformation? What signals the body that it's time to start developing these reproductive capabilities?
You're asking about the body's master control system for this.
Yeah.
It's a beautifully complex interplay known as the hypothalamic pituitary gonadal axis.
The HPG axis, heard of it.
Exactly. About a year before the visible signs of puberty appear, we start to see increased nocturnal secretion of powerful hormones called gonadotropins. These include luteinizing hormone, LH, and follicle-stimulating hormone, FSH.
LH and FSH, okay.
There's also a greater pituitary response to gonadotropin-releasing hormone, GnRH, from the hypothalamus. This whole cascade stimulates the gonads, ovaries in females, tests in males, a process we call gonadarche, ramp up their production of sex hormones. Estradiol in females and testosterone in males.
And these hormones, estradiol and testosterone, they really kick off some dramatic changes, don't they? What are the key transformations we see?
Absolutely. In females, estradiol is responsible for breast development, maturing the reproductive organs, and that characteristic fat deposition.
Right.
For males, testosterone drives the growth of the testes, scrotum, penis, and contributes to increased muscle mass. And here's something interesting. Both sexes also experience adrenarche.
Adrenarche, what's that?
It's an increase in adrenal androgens. These contribute to the growth of pubic and axillary hair and activate sebaceous glands. So, hello, puberty acne.
Ah, yes. Good times.
Right. Puberty is considered complete when an individual is reproductively capable. For females, that means their first ovulatory menstrual period, and for males, the first ejaculation containing mature sperm.
Okay, from this fascinating foundation, let's now transition into the fully formed female reproductive system. It's an incredibly intricate design. What's its core purpose, and where do we begin with its anatomy?
Its primary function is pretty clear. Produce mature ova, or eggs, and, if fertilized, protect and nourish the developing fetus until birth. When we visualize this system, we usually start with the external structures, collectively known as the vulva, or pudendum.
The vulva,
Yeah.
okay, like a protective gateway.
Exactly, a protective and sensitive gateway. Starting anteriorly, there's the mons pubis, a fatty mound covered with hair post-puberty, cushioning the pubic symphysis. Below that, we find the labia majora, two outer folds of skin and fat protecting the inner structures. They're actually homologous to the male scrotum.
Oh, interesting connection.
Yeah. Inside those are the labia minora, smaller, hairless folds that enclose a space called the vestibule.
And within that vestibule, there are some very important structures, right?
Indeed. It's a hub of activity. You'll find the introitus, the vaginal opening, the urethral opening, and two crucial pairs of glands: the Skene glands and Bartholin glands.
Skene and Bartholin glands, what do they do?
They secrete mucus and, interestingly, bactericidal fluid, vital for lubrication during sexual stimulation and, surprisingly, enhancing sperm viability.
Wow, okay.
And, of course, just anterior is the clitoris.
Yeah.
A richly innervated erectile organ, homologous to the penis, a primary site of sexual stimulation and orgasm. Wrapping up the external structures is the perineum,
The perineum.
the muscular area between the vagina and anus, providing essential support and elasticity, especially vital during childbirth.
That's a comprehensive tour of the outside.
Now let's move inward. The vagina. Right. The vagina is an elastic fibromuscular canal, typically about 9 to 10 centimeters long. It's truly multifunctional. Birth canal, pathway for menstrual fluid, site for intercourse. Its internal walls have these transverse wrinkles called rugae. They allow it to stretch significantly. A key insight here is its self-cleansing action, maintained by an acidic pH.
Acidic, right. Why is that?
Largely due to Lactobacillus acidophilus bacteria. That, plus a thick epithelial lining, especially during reproductive years, helps keep things healthy.
That acidic pH always strikes me as such a clever natural defense. Why is it so critical?
It's absolutely crucial. That acidic environment discourages most pathogenic bacteria from growing, making the vagina remarkably resilient to infection. Any disruption, like douching or low estrogen, can compromise this defense. It's a subtle but powerful protective mechanism.
Fascinating. Okay, from the vagina, moving deeper, the uterus. Pear-shaped, you said.
That's right. A hollow, pear-shaped organ that anchors and protects a fertilized ovum. It typically rests on the urinary bladder and averted, though variations are normal.
And its walls. You mentioned layers.
3 key layers. The perimetrium is the outer protective layer. The myometrium is the thick, incredibly powerful muscular middle layer, especially strong at the fundus, the top part, for pushing during birth.
Okay.
And then there's the endometrium, the inner lining. The functional layer of this endometrium is incredibly dynamic. It thickens and sheds monthly in response to hormones. That's the menstrual cycle right there.
And the cervix, the narrow lower part, acts as both a barrier and a gateway.
It absolutely does. The cervix acts as a mechanical barrier, protecting the uterus. Its mucus changes consistency throughout the cycle in this, unbelievable way.
How so?
It's thick and sticky most of the time, forming a plug. But around ovulation, it becomes thin and watery. We call that spin-barkite mucus, specifically to help sperm travel.
Spin-barkite, wow.
Yeah, this adaptability is truly remarkable. Also, a vital clinical point. The transformation zone within the cervix is particularly vulnerable to human papillomavirus, HPV, which is why regular pap tests are so crucial.
Right, for detection.
Yeah.
Okay, going upwards from the uterus, we reach the fallopian tubes. This is where fertilization usually happens.
Indeed. These tubes extend from the uterus towards the ovaries. Their fringed ends near the ovaries, called fembrio, create gentle currents to draw the ovum in after it's released.
Like little fingers coaxing it in?
Sort of. Once inside, tiny hair-like cilia and muscular contractions, peristalsis, move the ovum towards the uterus. The ampulla, the distal third of the tube, is usually a spot where fertilization occurs. A very precise journey.
And then we come to the ovaries, the primary female reproductive organs. What are their main jobs, and how do they differ from, say, sperm production?
The ovaries have two crucial functions: secreting female sex hormones and developing and releasing female gametes, or ova. What's really striking, and often surprising, is the difference in gamete production compared to males.
How so?
Females are born with their entire lifetime supply of primitive ova, maybe 1 to 2 million.
Born with them all. Wow.
Yeah. By puberty, this number drops significantly to around 300,000 to 500,000, and only a tiny fraction, maybe 400 to 500, will ever mature and be released during a woman's reproductive years.
That's incredible. Such a contrast to males. So, what are the primary hormones these ovaries produce?
Two main ones. First, estrogens, primarily estradiol, vital for maturation, secondary sex characteristics, bone density, even brain function and mood.
Okay.
Second is progesterone, often called the hormone of pregnancy. It's secreted by the corpus luteum after ovulation, crucial for maintaining the endometrium for potential implantation, relaxing the uterus during pregnancy, preparing breasts for lactation.
Speaking of hormones, let's connect this to the menstrual cycle. It's like a coordinated dance, right? Can you walk us through the main phases?
It really is a master class in biological coordination, usually 25 to 30 days long. We generally divide it into three main phases, reflecting changes in both the ovaries and the uterus. First is the follicular or proliferative phase.
Follicular proliferative, okay.
Here, follicle-stimulating hormone, FSH, from the pituitary stimulates ovarian follicles to mature. The rising estrogen levels cause the endometrium to proliferate, to thicken up.
Preparing for a potential pregnancy.
Exactly. Then comes the next phase.
Following the follicular phase, a surge in luteinizing hormone, LH, triggers ovulation, the release of a mature ovum. This marks the beginning of the luteal or secretory phase.
Luteal secretory, okay.
The ruptured follicle in the ovary transforms into the corpus luteum, which then secretes both progesterone and estrogen. These hormones further prepare the endometrium, making it rich with glands and blood vessels, really hospitable for implantation.
So if no conception occurs, what happens to that carefully prepared lining?
Well, if conception doesn't happen, the corpus luteum degenerates. Hormone levels, progesterone and estrogen drop sharply.
Okay.
This decline leads to the ischemic or menstrual phase. The starved endometrial lining is shed, resulting in menstruation. It's like a reset.
Makes sense. But if conception does happen?
Then the developing blastocyst secretes human chorionic gonadotropin, HCG. That's the pregnancy test hormone.
Right, HCG.
HCG maintains the corpus luteum, keeping those vital pregnancy-supporting hormones flowing and preventing the shedding.
It's amazing how precisely timed it all is.
Mm-hmm.
Are there other cyclic changes that go along with this hormonal dance?
There certainly are, and they can be very telling. For example, cervical mucus changes noticeably. It goes from thick and sticky to thin and elastic, that spin-barkite mucus we mentioned around ovulation.
Right, the scritchy mucus.
Yeah. The vaginal epithelium also thickens and thins. And here's a practical one. Basal body temperature, BBT. It increases slightly, maybe 0.4 degrees to 1.0 degrees Fahrenheit, during the luteal phase because of progesterone.
Ah, so that temperature shift indicates ovulation happened, useful for tracking fertility.
Exactly. Okay, we've delved deep into the female system. Now let's switch gears and explore its counterpart, the male reproductive system. What's its primary job and what are the key external features?
The male system's main job is pretty specific. Produce male gametes, sperm, and deliver them efficiently to the female reproductive tract. Externally, the core organs are the testes.
The testes. Essential, right?
Absolutely essential. They're like dual factories, producing both sperm and sex hormones, mainly testosterone.
And they're housed in a unique way, aren't they? Suspended outside the body.
That's a fascinating design choice, and for a critical reason. The testes develop in the abdomen and usually descend into the scrotum about 3 months before birth.
If they don't descend, that's cryptorchidism.
Right, cryptorchidism, it can cause problems, but the key insight is why they're outside. They need to be kept cooler, about 1 degree to 7 degrees Celsius below core body temperature for optimal spermatogenesis.
Sperm compression needs cooler temps. Got it.
Yeah. The scrotum itself, homologous to the female labia majora, is a clever temperature regulator. It contracts in the cold, relaxes when it's warm, all to maintain that perfect temperature.
That's a brilliant adaptation. So inside the testes, where exactly is sperm produced and how does it mature?
Inside, we find tiny coiled tubes called seminiferous tubules. These are the sperm factories. Between these tubules are specialized Leydig cells, which produce testosterone.
Okay.
After sperm are produced, they're not quite ready. They move into the epididymis, a comma-shaped, highly coiled tube. They spend about 12 days maturing there, gaining motility and fertility.
So they need that time in the epididymis.
They do. From the epididymis, the vas deferens transports them towards the urethra for ejaculation.
And what about the penis? Its functions and internal structure.
The penis, homologous to the female clitoris, has 2 key functions: sperm delivery and urine elimination. Internally, it's made of 3 compartments of specialized erectile tissue.
Erectile tissue.
2 corpora cavernosa and 1 corpus spongiosum, which surrounds the urethra.
Which brings me to the question, how does an erection actually happen physiologically?
It's a neurovascular event,
Right.
managed by the autonomic nervous system. Sexual stimulation causes arterioles in that erectile tissue to dilate, letting them engorge rapidly with blood. That causes rigidity. The erection is maintained because veins get compressed, trapping the blood. While it's largely involuntary, the brain can definitely influence it.
Makes sense. Beyond the external parts, what are the key internal male genitalia? The ducts and glands.
Good point. The internal parts include ducts and glands.
Yeah.
The ducts vasa deferentia, ejaculatory duct, urethra are the plumbing system for sperm transport.
Right.
And the accessory glands are crucial. The prostate, the seminal vesicles, and the Cowper glands. These secrete fluids that mix with sperm to form semen.
Semen isn't just sperm, then?
Not at all. The fluid is vital. It's a transport vehicle, sure, but it's also nutritious and alkaline, helping sperm survive the acidic female reproductive tract and stay motile.
So let's talk about spermatogenesis itself, that continuous sperm production. How does this compare to the female's fixed number of ova?
This is a fundamental difference. Unlike females with their fixed supply from birth, spermatogenesis starts at puberty for males and, remarkably, continues throughout life.
For life. Wow.
Yeah. It happens in those seminiferous tubules. Primitive germ cells called spermatogonia undergo meiosis to become spermatids, which then differentiate into mature spermatozoa, or sperm, each with 23 chromosomes.
And what role do those Sertoli cells play in this ongoing process?
The Sertoli cells are absolutely key. They're support cells within the tubules, like nurse cells. They provide nutrients and hormonal signals for the spermatids to develop into mature sperm.
So they nurture the developing sperm.
Exactly. And the whole process takes a fair bit of time, about 70 to 80 days from start to finish.
And male sex hormones, like testosterone, how's their production regulated compared to the female cycle?
Another big difference. Male sex hormones, mainly testosterone, are produced steadily by the Leydig cells, not cyclically like female hormones.
Steady production.
Right. Testosterone drives male tissue development, secondary sex characteristics, muscle and bone growth, voice deepening. It's crucial for spermatogenesis and libido, too. A constant, powerful influence.
We've explored both systems. Now, let's broaden out to a structure present in both sexes, but really critical functionally in females. The breast. What are they, biologically speaking?
The breasts are essentially modified sebaceous glands, which is kind of surprising.
Sebaceous glands, like oil glands.
Yeah, fundamentally. In both sexes, they have 15 to 20 lobes, and within those are smaller lobules. The functional units are tiny structures called achini, lined with epithelial cells that secrete milk during lactation, and subepithelial cells that squeeze the milk out.
So they're there in both sexes from childhood, but what triggers the big development in females at puberty?
Hormones, again. While they're latent in childhood, female puberty brings a huge transformation. It's an interplay of growth hormone, insulin-like growth factor 1, and especially estrogen that stimulates mammary growth.
And the large breast development is often the first sign, right?
Often the very first visible sign that female puberty has started, yes.
And how do female breasts continue to change during the reproductive years before lactation?
Well, during the reproductive years, they undergo regular cyclic changes, responding to the ebb and flow of estrogen and progesterone.
Ah, so they change with the menstrual cycle too.
They do. This hormonal influence leads to increased blood flow, more vascularity, and proliferation of ducts and acinar tissue. That often causes that familiar premenstrual fullness or tenderness.
Okay.
Of course, their ultimate function is providing nourishment for newborns. Prolactin stimulates lactation after childbirth, and oxytocin controls the milk ejection reflex. And breast milk, especially the early colostrum, is packed with immune components and nutrients. Vital stuff.
What about the male breast? Why doesn't it develop the same way?
It just doesn't. It typically stays in its childhood stage. Without high estrogen and progesterone, and with androgens like testosterone having an antagonistic effect, it remains mostly fatty tissue with an underdeveloped nipple and ducts. Though sometimes temporary enlargement, gynecomastia, can happen during puberty due to hormonal swings. That can be a concern for teens.
Right. Okay, we've covered development and peak function. What happens as we age? Let's start with females and the major event of menopause.
Menopause is, a universal developmental event for females, typically around age 51. It's defined retrospectively after 12 straight months without a period.
And the cause is declining ovarian function.
Primarily, yes, a dramatic decline in ovarian function and consequently a sharp drop in estrogen and progesterone production. It's a distinct biological shift.
That hormonal decline must have widespread effects, right?
Yeah.
Far beyond just reproduction.
Oh, absolutely. The effects are truly systemic. During perimenopause, the years leading up to it, cycles get irregular as ovarian function wanes.
Right.
Postmenopause, the physical changes are significant. Ovaries shrink, the uterus atrophies, breasts involute lose firmness. The genitourinary tract changes to vaginal shortening, less lubrication, higher pH.
Which increases UTI risk, you
Yeah,
said.
exactly. And thinning of the vaginal lining.
And the impacts extend even further. Mood, overall health.
Definitely. The rapid drop in estrogen is notorious for causing vasomotor flushes, hot flashes. Up to 85% of women experience them.
Wow, that many.
Yeah. Lower estrogen also contributes significantly to mood swings, anxiety, weight gain, skin changes like dryness and wrinkling, and, crucially, a much higher risk of osteoporosis.
Bone loss.
Right, accelerated bone loss. And also an increased risk of cardiovascular disease. And it really impacts health systemically.
And what about males? Is there a similar distinct event? Or is male reproductive aging different?
For males, aging brings changes, but it's much more gradual. Not a discrete event like menopause, we often call it andropause, or late-onset hypogonadism. It's a slower decline.
So they maintain reproductive capacity longer, but there are still physiological changes happening.
Precisely. Males generally treat reproductive capacity longer, a key difference. But they do experience a gradual decrease in testosterone production.
Okay, and what does that lead to?
It can lead to testicular atrophy, decreased fertility, some loss of muscle mass and strength, and often a reduction in libido. Physically, they might need longer stimulation for an erection, have less forceful ejaculation, and see changes in sperm concentration and motility. It's progressive and varies between individuals.
So ultimately, studying menopause and andropause really highlights what about our sex hormones?
They truly underscore the profound systemic influence sex hormones have on our overall health. Their impact goes way beyond just reproduction, touching bone density, cardiovascular health, brain function, skin, everything. Understanding these changes helps us appreciate the intricate balance that governs our well-being throughout our entire lives.
Wow, that was quite a journey through the structure and function of the human reproductive systems. Let's quickly recap some of the key insights we've pulled from this deep dive. We started right at the beginning, learning how both male and female systems differentiate from those homologous embryonic structures driven by genes and hormones that fascinating SRY override. Then we explored the hypothalamic pituitary gonadal axis, the master conductor for puberty and lifelong reproductive function.
And we dove into the specifics of the female system, the external vulva, the internal uterus and ovaries, and those coordinated phases of the menstrual cycle. Real biological precision there.
From there, we looked at the male system, continuous sperm production, maturation, delivery, and the role of those accessory glands in making semen viable.
Finally, we touched on the breast's development and function, crucial for females, and then looked at aging, the distinct event of menopause for women, and the more gradual andropause for men.
Thinking about all this, Consider this. What are the implications of really appreciating the body's own regulating systems, like that vaginal pH or scrotal temperature control?
Yeah.
It makes you wonder how disruptions from environment, lifestyle, maybe even subtle genetics can ripple through these systems, impacting health way beyond just reproduction. It really highlights how interconnected everything is.
It's true. This knowledge isn't just academic, it's about understanding the amazing, complex machine that is the human body and appreciating the elegance of its design.
We hope this deep dive has given you some great insights and perhaps sparked even more curiosity. From the Last Minute Lecture team, thanks for joining us on the deep dive.